All right, welcome back. So, in the last video, we were talking about paired t-tests and sort of the basic nuts and bolts, and also talking about all of the other t-tests and why why they're good and when to use them, right? So all of these t-tests, right? You can't just go out and do whatever t-test you want. It all has to do with the type of data that you have, right? So if you have two independent groups, you have to do an independent t-test. If you have paired groups, if you have the same group twice over some period of time, then you have to do a paired t-test, right? If you only have one sample, then you have to do one sample t-test, right? So you can't just go off and pick and choose your favorite one, because my favorite one is a paired t-test, but it all has to do with the type of data that you have. So in this video, I will show you how to do a paired t-test with something that you'll see similar to something you see on the test, whatever. So the general idea here is, with this, you can read it yourself, but the general idea is that there's a bunch of pollutant in the ground in a certain spot, right? And so they want to see if a certain method of removing this pollutant actually works, right? So what they did is they went to this one place, divided it up into 13 plots, essentially, and did the this new method of removing the garbage, the pollutant, from the ground. And they measured before they did that, did the thing, they did the new method, and then they measured the plots after. And they were measuring, essentially, how much stuff there was left over, right? And that's measured in milligrams of pollutant per kilogram of soil, okay? So you'll notice here that we have more information than we're kind of used to, right? So let's take it piece by piece. We've got the pre-removal of the pollutant from the ground. The sample mean of the pollutant in the ground was 54.35 milligrams per kilogram. Kind of a weird unit, but that's okay. And with a sample standard deviation of 15.65, right? So across these 13 points, the mean pollutant was 54.35, and then it varied by this much per plot to plot. Okay, so then they did the thing, right? They did the thing, and then after, like I think a year later, I think it says it in there too. This is also real data. Yeah, a year later, they came back and measured the pollutant, right? And they, in the same 13 spots, right? The same 13 spots, they found that the sample mean was 15.52, and it varied much less. 5.96. Okay, crazy. So this is the nuts and bolts, right? This is the foundation that we're going to be working from. But what we need, though, is we need sort of the pre minus the post. We need that mean, okay? And we have that down here. We have that. That's calculated for us, right? So it straight up is just 54.35 minus 15.52. That's this value, and that's fine, okay? But this value, the standard deviation, sample standard deviation of the pre minus the post, or the post minus the pre, however you want to word it, is 12.46. In fact, actually, I think, yeah, I've got this kind of backwards. If we did post minus pre, these would both be negative values. Really, this is pre minus post. What this is saying, it's totally fine either way. But this sample standard deviation of the pre minus the post is not 15 minus 6 here. It is not that. Okay. It's also not the mean of these two things. It's a totally different formula that we've never seen before, and we're not even going to worry about it, okay? I'm just going to give it to you, right? So everything here is the foundation that these two values come from. These values down here are what we actually need, right? So you always see it sort of in this situation. You got to know which one to use, right? And it's always going to be the ones towards the bottom, more or less. If you're just trying to take this class for the test, always look for the stuff at the bottom. But do know that this is much different than these two. Okay. And then we have the number of pairs is 13, which is set up here, right? So in total, they measured 26 things, but half of those are the same, right? They're just going from Plot 1, measuring again after some time. Plot 1, right? Okay, cool. No doubt. So let's do it. What do we want to do first? Well, we need to... So the research question, step 1, is, did the new method work, right? What's the effectiveness of this new method? Okay, so great question. I'm not going to write that out, but we will write out step 2, because this is where it gets kind of fun, right? Because we can write these in a few different ways, right? Hypotheses. Okay, so our H naught, or null hypothesis, in English, let's write it out in English first, is that the new method does nothing, right? So even if we did the new method, it's almost like the result would be as if we didn't do anything, right? Okay, and then the alternative hypothesis is that the new method, and instead of me I'm just going to do this, the new method does something. Something, right? So already, if we just read the question 2, we're looking at determine whether the effort to remove PCB, which is that pollutant, resulted in a statistically significant difference, right? So we're not looking at it, is it less, right? Or is it more? We're just looking at it, did it change, right? So did it do anything, right? Okay. So we'll come back down here. That's the English hypotheses. The null and the alternative from a mathematical point of view is that the population difference is 0, right? The population difference. All right. So when we try to, we're talking about the method, right? But we're more or less sort of using these plots, right? This PCB is the pollutant, right? We're looking at the plots affected by this type of pollutant, right? And then the mean population difference, right, is not 0. Effectively the same thing. We're just using effectively the same thing as the independent samples t-test, but we're using just slightly different notation, and that's okay. That's totally fine. Okay, so let's move on. We'll go into a new page here. Step 3, we got to calculate that test statistic. Cool. Whoop. Sweet. Okay, so our t value, still working in the t world, pretty cool, pretty great. Equals, okay, so we got to take our mean difference, right, which is given to us, divided by standard deviation, sample standard deviation of the differences, divided by the square root of the number of pairs that we have, right? That's that, right? So our, let's see, our D bar is, what was it? 38.8. 38.8. Oh, I assume that it's 0.80 because they were that precise. Whatever. And then our standard deviation of the differences is 12.46. Milligrams per kilogram. Okay, and then the number of pairs we have, if I recall correctly, is 13. Now, that also means, we'll just go ahead and write this out, our degrees of freedom is 13 minus 1, which is 12. Cute. All right. Sweet. So let's plug and chug here. Let's plug and chug. So T equals D bar 38.80 divided by 12.46 divided by the square root of 13. Okay, 13 here. Not looking at degrees of freedom for this equation, only looking at the number of pairs, right? And we'll put all of this under parentheses too, just so you know we're not getting confused with the order here. Cool. So you work that out, and that turns out to be, and I've got it here. Beautiful. This turns out to be 11.227. So we'll say 2.3. Okay, that's a huge test statistic. What we've been doing, it has been like in the world of 2s and 3s and maybe 1s and whatever else. Effectively, what this is saying, and let's take a step back and realize what this test statistic is really doing. Very similar to the Z world, when we were comparing sort of standardized scores. So and so is 2.5 standard deviations below the mean. What this is saying here is that our data is 11.23 standard deviations away from where we expected it to be. Whoa, right? Pretty big. Okay, so we are 11.23 standard deviations away from where, quote unquote, we're kind of supposed to be, or where we expected it to be, right? And that's what we've been doing with these test statistics this whole time, right? It's just saying in standard error units, standard deviation, same sort of thing, saying that we are that far away from our expected value. Sometimes if it's close enough, right, if it's within that 95% sort of world, then we say whatever, if it's in the area that we expect it to be. But if it's outside that area, right, then our p-value is going to be really small, right? We did not expect it to be that far out there. That's sort of the idea with these test statistics. Summarizing and standardizing our data. Cool. Okay, anyway. So we're this far away from where we expected it to be. Pretty crazy. So we'll just go in here. Let me get rid of this from the last example. And let's put in everything we need. So let me actually write this out too. Step 4. P-value. Butte. Okay, so 11.23, how many, we've got 12 degrees of freedom, and we have 11, check this out, 2 3s, two-tailed option. Can you even see it drawn? I do not think so. Yeah, you can't. Okay, so what this is saying is that we're 11.23 standard deviations away from where we expected it to be, which is wild. But check out the p-value. Now, it's throwing out a 0, and this is not an error. It's throwing out a 0 because it is so far away. It's like way far. I guess it's way far out here, right? So the area is really small. The area is not 0, but it practically is, right? The chance or the probability that seeing our data is totally due to chance or due to randomness is super low. So in this situation, here's what we would say. Our p-value is super low. So instead of saying like p-value equals 0, because it never is 0, it is never ever going to be 0. It can be close to it, but it'll never touch it. What we're going to say here is that's below. It is less than 0.05, but it's also we can even get more kind of granular with it. We'll say that it's less than 0.01, and you'll see this sort of notation used a lot in research, where they don't throw out the actual p-value, but they'll just say it's less than 0.05. Now, sometimes, or 0.01, sometimes that's fine. Sometimes that lets us know, like in this case, our p-value was stupid low, okay? But sometimes, if your p-value is 0.049, you can say that it's below 0.05, right? Even though you're so close to your alpha level that you might say that there really is no difference between the two things, but you can still report it. You can still report a significant difference, right? You can kind of tweak it in that way, which is not cool. You should not do that. Anyway, so we're saying that it's super small. We can even say, you'll see it like this sometimes, crazy low, right? Crazy low. We'll just leave it as that though. We'll leave it as that. I'm satisfied with that. Okay. So step 5 then, is we got to conclude what we found, right? So since p is less than alpha, what do we do? Well, and we also assume, I don't think I said it earlier in that one either, but we also assume that alpha is 0.05, right? Easy peasy. Because we're going to make a confidence interval here in a second too. But since p is less than alpha, right, we are going to reject the null hypothesis that the mean difference, the mean population difference is 0. We reject this idea. We reject it, right? Okay, so that means that we have significant evidence we'll just say the English kind of translation here. We have significant evidence that the new removal method works, right? But by how much? Because right now we only know that it does work, and we know that there's a difference. It kind of decreased there quite a bit. But let's actually figure out the range of values that the population could hold, okay? So we'll come over here and we'll make everyone's favorite 95% confidence interval, okay? Okay, and then, so that formula looks like it's d bar, or we could go, because we're effectively trying to estimate the population mean difference, the mean difference. That's going to be plus or minus the t crit, and then the standard error. Okay, so let's write d bar. D bar is given to us, so that's 38.8. Whoops, 38.80. Our standard error is just the sample standard deviation of the difference divided by the square root of n, which was, what was that? Hold on, give me a second. Okay, so that was 3.46, right? So all that is the denominator here. So you could just kind of copy and paste that out of your calculator or out of your phone, computer, whatever, and just run that itself. And then you'd get 3.46, okay? And then all we need now is our t crit. So what do? Well, we go back to our friend, the t distribution here, this little tool that we've got. We've got the degrees of freedom already in there, but let me take it out. Okay, so it's totally blank, right? Our degrees of freedom, we had 13 pairs, so that means our degrees of freedom are 12. Got that. And we want a 0.05 is our alpha, right? And that's going to spit out 2.178, so we'll say 2.18. 2.18. Very cool. Very cool. Okay, so let's figure out the lower bound, and then we'll put the upper bound kind of down here. Okay, so then let me get this out. Oh man. Okay. Okay, so that is going to be 30. Let me do it in a different color here. It's going to be 38.80 minus, right? We're on the lower bound, so we're subtracting. And let me be very explicit with my order of operations here. 2.18, right? That's the t-crit times our standard error, which is 3.46, sorry. Multiply those together and then subtract. And that turns out to be 31.266. So say 31.2. Let's just say 31.23 or 31.3 milligrams per kilogram of soil, right? Same deal here. So 38, that's our D bar, 38.80. And then plus, because now we're in the upper bound. I have to say that for myself. And then 2.18, same deal, right? Same deal. And that turns out to be 46.33, right? You might have some different rounding things on your calculator. Totally fine. Totally fine as long as they're decently close. We'll leave it as that. Milligrams per kilogram. Sweet. Okay, so we'll come back over here. Our 95% confidence interval is 31.3 to 46.3. And let's take a note again at our D bar, right? So we're looking at differences. Okay, we're not looking at new means of groups or whatever. We're looking at the mean difference, okay? So the population for plots that were affected by, or plots of land that were affected by this pollutant, this PCB pollutant, with this new method, if you were to do this new method, on average, the population probably the difference between the pre and the post, before doing the method and after, would most likely be, we're 95% confident that it's going to be between 31.3, right? So the difference is, the smallest difference you'll see would be 31.3 milligrams per kilogram, up to 46.3 milligrams per kilogram. So we are 95% confident that the true population difference after treatment is between 31.3 milligrams per kilogram to, actually, we'll not say 2, we'll just say between and 46.3 milligrams per kilogram. If you can read my handwriting, good Lord, that looks awful, and I'm so sorry. Trying to be fast here so I don't take up all your time. So we are 95% confident that the true population difference after the treatment, or from the treatment, is between 31.1 milligrams per kilogram and 46.3, right? So we estimated the actual population with this, which is wild, right? So if we were to go to every plot of land that is affected by this pollutant, try this new method of removing that pollutant, we would see that on average we would remove this amount, right? And the difference would be within that confidence interval, which is, I think that's super cool. I think that's wild that we can estimate it and get it within a pretty decent range in this case. Cool. So I'm gonna have a few homework assignments. Well, not a few. I'm gonna have a couple of questions about this idea, right? And I'm gonna ask you. I think, I'm still kind of mulling it over. I'm going to ask you to do a 2-sample t-test on this data, even though it's not appropriate. It's not appropriate to do a 2-sample t-test when the data are paired, right? But you'll notice that you're going to get slightly different results when you do this. In fact, you'll get a better, closer estimate with the 95% confidence interval with the paired data than you will with the 2-sample test, which is wild, I think. The 2-sample test is not as strong as this, which is why we prefer paired data. Pretty wild. Pretty cool. Okay, so with that's t-test, y'all. We just covered a lot of ground. So if you have questions, let me know, and I will see you when I see you.